four-letter word, PFAS. Those four letters contains hundreds of different substances. In this short video, I will go through the basics, what PFAS is, and also how do you synthesize different types of PFAS substances. And to be clear, I'm not an expert on PFAS. I'm doing this video because I find it very interesting and I have some chemistry background which makes it even more interesting. But let's go on with the PFAS story. PFAS substances are very stable compounds. Furthermore, and importantly, their properties are very, very helpful for us in our daily life. As you can see in this slide and the circle here, you have firefighting foam. And this is probably the most known PFAS source. But basically in everything we do in our daily life, we will come in contact with PFAS substances. And herein lies the problem. They're very useful substances. However, they also poses biological risk because they are very stable and will be in our environment for very long times. And there is also a question, what happens when they get into our body or in animals or in the sea, air? How are they decomposing? Will there be side effects when they're decomposing hazardous products? So the problem is products that we use hourly, every day, but also can pose a risk for us. You have two main groups of PFAS substances. You have the non-polymers and you have polymers. Looking at the non-polymers, you have hundreds of different types of PFAS substances. But I would guess here you will also find the most well-known PFAS substances that is in the firefighting foam. And in a moment we'll look on how to make one of those substances. But before that, let's have a look at the other group of PFAS, the polymers. Here you can see your frying pan where you have the non-stick material made out of PFAS. Also you have the very well-known Teflon tape, which is used for sealing couplings. And also you have, in this example, a PVDF hose, a hose that is extremely resistant to different very aggressive chemical substances such as sulfuric acid. But now let's have a special look at one substance called PFHPA, as we noted in the yellow box here. How is that chemically made? Our starting point for making the PFAS substances is alkanes, and they consist of carbon atoms and hydrogen atoms. Now let's make a simulation. Here we introduce 3 carbon atoms, add some bindings and some hydrogen atoms, and voila, we have our first example of an alkane, which in this case is known as, well, lighter fluid, or more correctly, propane gas. So this is a short alkane. But now we are going to construct a PFAS with 7 carbon atoms, and we now add the hydrogen atoms and we get heptane liquid. So this is now our starting point, and heptane is a solvent that I've used a couple of times when working in the organic lab. We now have the solvent heptane as our starting point, and now we're gonna simulate a synthesis of PFHPA, or perfluoroheptanoic acid. The heptane consists of 7 carbon atoms, all surrounded by hydrogen atoms. So the first thing we need to do to get our PFAS substance is to change the hydrogen atoms on the last carbon in the heptane chain to an oxygen and a hydroxyl group. And this here N group is called a carboxyl group. And getting that takes several chemical reactions. So starting with the heptane, and here you have the last group, and through a number of chemical reactions you get the carboxyl group on the end of the heptane chain. Now we are ready for the final step in getting our PFAS or PFHPA. Now we are going to replace all the hydrogen atoms that are left on the 7 carbons. We're going to replace them with fluoride atoms. And we are doing this with a method called electrochemical fluorination, or ECF. And this is the method that was used when PFAS first being produced in the 1950s. So using the ECF, you will get your final PFAS substance. And in our case, starting with heptane, we end up with PFHPA, or perfluoroheptanoic acid. Now let's look at what makes the PFAS tick, or what decides the properties of a certain PFAS substance. Here you have covered in the blue area carbon and hydrogen atoms. That's the tail of a PFAS molecule. And then we have the functional groups. And the functional groups is made up of positive or negative charge, but you also have a non-ionic tail. Meaning an anionic tail, you see here on top, you have a carboxylic group, which is negatively charged. Cationic, you have the hydrogen and nitrogen, which is positively charged. And then you have something called zwitterion, which is a little functional group containing of a positively and a negatively charged part. In here you have the nitrogen, which is positively charged, and on the carboxyl group you have the oxygen, which is negatively charged. And as I mentioned, or we went through before, depending on how you synthesize what type of PFAS you want, you will decide its property by this functional N group that is attached to the carbon tail, so to speak. The anionic, cationic, zwitterion, or non-ionic properties will, of course, be very important for how you remove the PFAS from water or from soil. We now know that there are hundreds of different types of PFAS substances, and very importantly, they are all around us. So when you now need to sample water, for instance, you need to be quote unquote damn careful on how you sample, what you wear, etc. Because the PFAS substances are most of the time in very, very low concentration, nanograms concentrations. So the sampling puts a lot of emphasis on doing it correctly. And on the YouTube, I found a video which I will post a link to in description field. And this video I think you should look at, and then also remember what we just spoke about in this video. On the next slide, I will show you the references I've used for this presentation. So with that, I hope you, if you're interested, stay tuned for the references. Otherwise, see you in the next video. Take care. Bye bye.